Welcome back, everyone. My name is Daniel Sills, and this is video check-in 2 for the UofL course Applied Robotics. For those of you that don't know, we are building a submersible robot capable of accomplishing a series of tasks, including the first one that we are targeting, which is just simply submersion. We want to be able to submerge the robot and bring it back to the surface on command. And so in this week's agenda, I'm going to go over some design updates, some revisions I've made, the 3D model I've started, the internal chassis that I have begun printing and testing, and as well as in the back half, I'll go over some electronics updates, including discussing PPM control and the motor control scheme. Alrighty, so in last week's video, I proposed these two sketches. This one is wildly out of scale if these are supposed to be 2-inch tubes and 4-inch tubes and things along those lines, but I think it looks pretty. So I'll keep it around for now. It also illustrates some points pretty well. So this is more to scale. So this is 2-inch and 4-inch and 2-inch, and then this is 6 inches long. I have since come to the realization, since making last week's video, that with the layout that I would like to implement, we have an issue with the size of this component. This is the removable end cap for the PVC pipe, which is critical to the design, and it is quite a bit larger than I expected it to be. And so we are moving from 6 inches in length to 8 inches in length. And so that updates our drawing to look something like this, and then here's the CAD design that I've started working on. The goal of this CAD design as I continue fleshing it out and detailing it is both to be able to generate specific 3D printed components that I need for structural purposes, but also going down the line to be able to generate a simulation of the robot. So it's in very early stages, but I do have a couple more components that aren't shown in this image right there, such as this one. Last week I mentioned this drawing, and this drawing is actually fairly well to scale. And I discussed this component, which everybody I have been corrected says does not look like an elephant at all. But it's okay, I never have to reference this again because now I have the CAD drawing. And so the goal of this is to provide some internal structure. This is just a testing design at the moment, the goal of which is to provide the necessary offset for 3D printing to give it a snug but not like get stuck level of fit in there. The goal of these would be to make them modular where they could connect together. So we would have one of these that would house the Raspberry Pi, another one of these that would have the camera module on it, and then another one of these that might have the ESCs on it. So I have currently started printing this test fitting one. And like I said, the goal here is to determine the amount of tolerance that I need from my personal 3D printer in order to get the fit that I'm looking for. I want these components to be able to slide in and out, but to not necessarily shift around within the body of it too easily. So now let's move on to electronics. This is all robotics. Now let's do electronics. I'm going to talk about progress, roadblocks, and the plans that I have moving forward. First, we're going to start by talking about PPM, pulse position modulation. This is common in RC applications and the communication method of both ESCs that I plan to deploy to control the 4 motors. It's an alternative to PWM, and it's stated to have a higher signal density, but I don't entirely understand how that works, and we'll get into that here in a little bit. So if you take this modulation signal here at the top and convert it to PWM signal, the thing that's constant on PWM being pulse width modulation, something a lot of people are more familiar with, pulse width modulation has a standard cycle time where each of these ups on the waves are a set distance apart, and typically that's the clock of whatever you're controlling, really, but that can also be synchronized to other devices. Well, in pulse width modulation, those are constant, and the width of the signal is what's changing. So as we reach our peak here, we have our longest width here. Well, in PPM, or pulse position modulation, you're actually changing the position, but you're keeping the pulse the same. So each of our downstrokes on the PWM signal becomes our upstroke on our position signal, and these are equivalent widths all the way along. They are just at different positions. And so our timing signal here is actually not synchronized at all. It is simply the width between these. But whenever you start talking about adding greater signal densities together, you do end up with what are referred to as frames to describe the PPM pulses. The problem here is the equipment I have is very efficient at making PWM signals, not PPM signals. So we have a few potential solutions. The number one solution that I'm considering right now is to do PPM generated directly from the GPIO. If I can get this working, it's by far the easiest solution. The concern that I have is, will this limit future GPIO use, such as the quick connectors as a form of I2C that I wanted to use, or the PWM hat that I was planning to use? If it limits those things, then obviously this is a no-go. And these are way more important to me than avoiding these. So the second solution that I want to explore is, and I've actually already explored this one a little bit, and I'll talk about that more in the next couple slides. The second solution that I would be interested in exploring is PPM generated by our Arduino. Arduino has a library, PPM encoder, that can do this, and I have seen several things on forum posts and things along those lines that this works pretty well. I do own an Arduino, so this would be free as far as the cost of the system goes, but it would increase the internal complexity. An Arduino is a large component, and so we would have to find space for that inside of the robot. And then the final option, which would reduce this higher internal complexity, but it's not free, and maybe it's the simplest option. I don't really understand how these work, but it is a PPM converter. It seems that they are better at doing PWM to PPM, not necessarily PPM to PW. Yeah, like I said, I don't really understand them. I would need to do more research on them. I don't understand how you can have the high signal density that I was talking about previously on the PPM. So I would need to figure out how to daisy chain my components together in order to utilize this multi-channel PPM system. Whereas in this, I could just have a direct relationship where each PPM is different, and so I can have a direct PWM or just control logic sequence between my Arduino and whatever component I need to control. I'm leaning towards this option. I don't think it's going to be a big deal to find extra space inside of the robot, but we shall see. So here is a time lapse of me soldering up the components so that I can talk about this. So feel free to watch the time lapse, and I'll interject to tell you about my shitty soldering here in a couple seconds. So this is the layout that I've already attempted. So this is the ESC direct to the GPIO pins. The GPIO pins of the Arduino are not specific here. You can really use any GPIO pin that you want. They're only on-off circuitry anyways. So you connect the signal wire and the ground wire from the ESC to here. ESCs have a plus 5 volt return that we are going to ignore. It is never good to feed voltage back into your Raspberry Pi, and so we are ignoring that label. Cool, good for you. And so then you feed a battery supply direct into the ESC, and that goes to the pump motor, or that controls the pump motor, and it will also control our thrust motor if I can get this working.
Okay. I'm going to plug these two cables into the ESC. That'll power on the ESC, assuming this battery is okay to do that. I really don't know anything about this battery, so that's kind of a risk. But then The ESC will be on, which means that it can receive input from the Raspberry Pi, which should have a program running to control it properly, because I'm pretty sure this communicates over PPM, not PWM. And then we'll see if the pump runs. So let's plug it in and hope nothing explodes. That would be really dramatic and bad. Oh, we've got a power light on. We've got a power light on. Alright, I'm gonna run this program. Are you gonna sing or anything? Cool, nothing happened. That's okay. That's not the end of the world. Okay, so I sat and tinkered with the setup for like maybe another 20 or 30 minutes. I'm gonna need to get an oscilloscope on it, or at least a voltmeter, or set up an Arduino that I can do some analog checks with or something. But in the meantime, here's the battery straight to the motor. I'm sure that's not bad for anything. Yeah, it runs. Woo! Everybody clap.
And so finally, future work. Continue to receive hardware. I have not received all of the hardware that I ordered last week, and so the goal is to hopefully get that finalized so that I can continue construction, or start on construction actually. The last big thing that I need to decide is how I'm going to do the clear end cap for the camera to see out of. I've seen some options such as using, what are they called? Such as using security camera lenses. These are domed lenses that you can get in some standardized sizes. So I would need to find a way to mount those and then seal them as well. Sealing, I don't think would be a huge deal. I do have some Gorilla Glue sealant, so that would be great. And then get the pumps running. This is the big thing. I want to test the Arduino library. If that seems simple and fairly robust, then I might just go that direction, just to make it simple on myself. So I'll see y'all next week, and hopefully I'll have more to show. Thanks.